Okay, so before we talk about homework 2, I will quickly mention a little bit on the stochastic gradient descent for this part. So you can see, so this is a quick summary of SGD. So that can compute a gradient, but update this weight matrix W on a very small batches of the training data. Instead of using the whole training set itself. So that means at each iteration, my weight update is noisy. So that means it might take up like more steps along the weight. And we think about it, we take one step for each batch and versus one step and versus, so each epoch. But ultimately it will lead to fast converging because calculating one tiny and a mini batch or even 1 point gradient, it's much more efficient than calculate the gradient for the whole batch. So this is the comparison table that we have. For the gradient descent, it is slow for large data. In terms of time per iterations. For total time to converge for large data, it will be slower. The total time to converge for large data in practice is usually really slow. It is also very sensitive. It's less sensitive to the parameter in these cases. But for the stochastic gradient descent, it's always fast. In theory and in practice, but it will be very sensitive to the parameter. So because we have very noisy and the weight update. So this is a very simple examples in terms of like logistic and the linear regressions. And so we know, for the linear regression, so we have this analytical solutions, but here we're just using the stochastic gradient descent to demonstrate this idea. So basically, the whole idea is right here. So we randomly shuffle, this data set. So this K is, and we have the number of case like epochs, and for each epoch, and we're going to iterate through for all the data from 1 to m by taking this and a stochastic gradient descent. And basically right here, and with this stochastic gradient descent, you will run through this whole data set 1 to 10 times, depends on how you choose the K. And also, and it depends on how fast this data is converging and how large your data it is. So in this sample that we have, and we will have like 50,000 data, and so we know this is like straight line. This will be really quick to converge. So first things we need to reshuffle this data, and but for this particular example, this is not strictly necessary because data is already in random order. But of course, if you work with image and other things, you probably need to reshuffle it. That would be helpful. So, and we run, this stochastic gradient descent algorithm, and you can see this whole progress. We can take this cost measurement at each, step, and every every 10,000 steps, we are going to get average cost for like last 10,000 steps and append to this. So we will run this entire list 10 times here to ensure this whole thing has very and average values. So we can actually and saw like how this things is, and it decreases with the with the cost. You can see, and we have run this like 10 to the 6 iterations. So this whole cost and it dropped very quickly, and then like after so initial dropping, it will start to fluctuate. So you can see right here. So at this point, I think we already reached certain like local minimum here, but because our update is always stochastic, so that's why it will be fluctuating around this local minimums. So that will be good enough. And of course, here we are taking the constant, and we are taking the constant like learning rate, which is just give you some like heads up. But usually if you really want to converge to the local minimum, so this alpha right here has to go to 0 asymptotically, and otherwise you will be just like bouncing around this local minimums. It will never actually converge to this like, I mean, that local minimum that you wanted. So this is some heads up that you and you need to know here. Okay, so that's just a quick update, but this is really up and really the important part. I want to talk about Homo 2. Homo 2 is a little bit theoretical, and again, I would suggest everyone to start early. So there are 3 problems. The first problem is about the bias variance trade-off. So you can see right here, and theta here is some unknown true means of like n Gaussian distribution. We haven't talked about this in, the past. So this is basically repeat everything we already did, and you just go through and the math and by yourself. So we get some like vector x, and xi is some and follow some distributions with a mean of and the theta I and the same and the variance sigma square. And we assume every Gaussian distribution here has the same variances and is independent, but the means will be different. Our job is to find estimated theta hat to minimize this expect error of which is basically the testing and the expect MSE. So basically all the expectations are taken with respect to the random draws of xi's random variables. All right, so first things first, this is like bias variance trade-off. We already talked about this. This whole derivation is very straightforward. I already showed that in the class. You just need to follow this math. But the issue is if we only observe one data, which is x right here, and obviously that would be the most like natural choices for the estimator. So you calculate the bias and the variance for this one single natural estimators. And you can also try a shrinkage estimator. That means I'm going to times 0.9 of the x value here. Then you do the same thing for the bias variance trade-off. It's kind of interesting. And obviously we intentionally bias this part. It turns out it's possible. There will be some situation that this like intentional shrink and a shrinkage estimator will be even better than this natural estimators, right? So you need to find a condition that that kind of situation happens. So you need to find a condition where like natural estimator is better than a shrinkage and vice versa. All right, so and to be frank, that's pretty straightforward. And the part, it should be done and pretty much quickly. Okay, the second part is on the kernelized regressions. And basically the whole homework 2 is still stick with and the regression part. For the kernelized and regressions, and you can see everything here is just being, and there is no skeleton of the code. You actually have to and program everything and from scratch by yourself. First things, you need to generate data. You need to generate data by yourself this time. So, and you have n equal to 30. So basically we have 30 points, and f star, which is the ground truth, which is 4 sine pi x times cosine 6 pi x squared. This will be like some oscillations you should be able to see. And you want to all these xi to be drawn uniformly and at random from like 0 to 1. So you can see at each draw, this value will be different. You should see some fluctuations with the different values. And you have this yi, that will be your ground truth from this f plus some epsilon, and you are adding some like Gaussian noises. And this Gaussian noise is standard Gaussian right here. Okay, so here is and then we are defining the true error and the training error. So basically respectively, so we have I mean, this is train and a true error, and obviously we don't and usually know that, but and we are using this and a training error right here to make some approximations for this an error right here. Our goal is to using kernel ridge regressions to construct the predictors like that. I already mentioned about this in the, so in the class, and how to solve this alpha head right here. In fact, you can find out this alpha head analytically by yourself. And basically, this prediction will be f head of and the kernel. So this right here is actually a vector because and if you plug in of x, and this whole thing is basically a scalar. But if you spend all and all the like xi from 1 to the n, that becomes a vector. So you can rewrite everything and here into the inner product between the alphas and the k's and the kx right here. All right, so like big K right here is a kernel matrix you can calculate by yourself. And this lambda right here is some regularization constant. So in the like class so we already show you how to calculate this so analytically. Here, and what you're going to do is you are going to, and of course and there are a lot of parameters and you need to choose, for example, what lambda you should be choosing, right? So that would be something that you need to use in cross-validation to find it out. First thing first, and you are going to using this leave one out cross-validations. So I didn't specify what is that explicitly, but I'm just trying to let you know. So we have a k-fold cross-validation. So the k-fold, a k, and say here is k equal to n minus 1. That one means I'm using n minus 1 data point to train and make a prediction for the remaining one, right? So that would be, and then we rotate this and n minus 1 times, and we rotate this, n minus 1 times to ensure, and to ensure every point is being, so sorry. So leave one out cross validation is the cases, then k is equal to n. So that means n here is 30, then you choose k equal to 30. So that means you are going to using 29 points and to train and leave one out to test. You do this 30 times such that each point will be test the data set. The validation data set at least once. So this is something called and leave one out cross validation. Usually this will be very expensive, but this is okay for this cases because our data set is super small. So you're going to work with two different kernels. One is polynomial kernel, it's right here, and the second is a Gaussian kernel or something called radial and a basis kernel right here. And of course, these are all like hyperparameters you need to be choose. Right here, gamma here, that will be, you can using this like heuristic and a gamma, which is inverse of the median of all these square distances and all together. So you can actually calculate this lambda just based on the data that you already have. And you can, and I strongly recommend to using either grid search or random search, but you cannot using scikit-learn here. You actually need to implement this algorithm from scratch. So these, and I give you the range that you should search for. The lambda will be range around 10 to the minus 5 to 10 to the minus 1. D will be the range from 5 to 25. In this case, and a gamma, you don't need to do any hyperparameter searching because you can using this heuristic. All right, so, and that's the thing that you need to be doing. So you're going to report this value of D, lambda, and gamma for both kernels. And also you want, and you want to like calculate this and this training errors as well. Okay, so for both methods, you have like being fitted using polynomials, and you can be fitted with this Gaussian kernels. And these are all functions used, and these parameters, I have a parameter you found previously, and you actually want to do some plot with those and with those functions that you learned, with these two functions that you learned, you plot this original data you already did, you plot this true f, and you also plot this f hat, right? So everything is just and being defined in a fine grid from 0 to 1. Then you plot these two functions. Okay, you make two plot, one plot for each functions. So and you can compare. So you can actually compare. So the result. Okay, so this is very important. So this just gets you to compare with the two possible kernels on the polynomial is kernels and versus the like Gaussian kernels. Okay, so with that you can actually learn everything and you actually implement everything from scratch for both cases, such that you have a good understanding of this kernelized and regression problems. And in particular, all these grid search and random search, you have to implement by yourself. So this is extremely important part. So you can have a good understand on what scikit-learn is doing is underneath. Okay, last question. It's a little bit long, but it's a little bit theoretical. But if you follow this one by one, and you can have a good understanding what is going on, and later on you will find out and you really appreciate and this and HOMO problem. This problem is going to answer why HOMO 1 question 2.4 and works so well. This is very important, it turns out. And this kernel method, such like and the logistic regression we are like working here, is considered very memory-based learners. It's rather than learning a mapping from a set of input to an output, they basically remember all the training examples xi and yi. Then what they do is learn some corresponding weight for them, like what we are doing right here, right? So, and what they do is they try to learn a weight for them, and for all the training like examples. So the key here is we need to learn this weight vectors W1 to Wn. Then we can make predictions for those unseen samples just using this kernel functions between training samples and X right here. The reason that is attractive is because it fully and rely on this kernel trick, and all these positive definite functions kernel and the function K is basically can be calculated or defined using some like inner product between data points. So that's why this whole thing and Kx and X prime here can be calculated very efficiently. So that's why the kernel trick will work. So that's why the kernel trick is a very efficient way to learn a decision like boundaries in the high dimensional spaces. And also this kernel trick can still be very expensive for large data. And for large data, think about the problem that you work with on question 2.4 in the like HOMO 1. You have a data of 60,000 data, right? So that's really a lot of like data. But think about if we want to build a matrix of 60,000 and 60,000, and by 60,000, that will be a huge amount of matrix need to be calculated. So that will be memory very intense. So you can see this is very memory intense algorithms through the data, because you need so you need evaluation of this kernel matrix, and of course it grows like quadratically to the data size of n. So and what you can do, in fact, what we already did is we are going to create some like feature mapping and provide this kernel tricks. So and what we can do is suppose we can approximate this kernel functions as inner product of two vectors. Mathematically speaking, is we want to find out such kind of mapping Z that the kernel of P of X and X prime actually can be approximated. As we know, this is equal to phi X and phi X prime. I hope this could be an approximate to like ZX and ZX prime. Why this is important? Because I mean, we know to calculate for this part, for all the data, that will be really expensive. But if we can take this mapping and to lower, I mean, the cost and of this memory part, that will be and really important. So with that an approximation, we don't actually require the kernel trick to calculate this phi x and phi x prime for this and the kernel values. Instead, we can approximate it directly, compute this inner product of ZX and ZX prime. So, and what does that actually mean is we can transform our predictions from this and KXI of X into this kind of Z and ZXI and ZX right here. So this can be written as in this form right here. So, but Z right here could be significantly smaller than the dimension of the N, right? So we don't, and here we assume this D is in the dimension of D. So that means my dimension of D right here could be significantly smaller than the dimension of N. Then this calculation, it will be much more efficient than and work directly on this and the kernel matrices. Right here, we assume this functions has this kind of form as sigma of mx plus b right here. This is kind of approximate, I mean, this logistic regression. But the key here is, and you can see, I mean, why, I mean, this is important because evaluating this whole thing, in general, this and omega I, it will not be sparse. On the other hand, the right-hand side is just required just to compute this whole thing, will be dominated by just calculate the D by D matrix vector product. Then we can just do the inner product with the beta and with the Z's right here. So this total computational times, I mean, for the left will be scaled and linearly with N, but right-hand side, it only scale with the little d and the big D's. So, and what does that means is we can just train everything here and we can save and a lot of and a computational cost if we assume our and a big D or small d is significantly small than the N. This happens in the previous homework. I want to remind you, this D here is a couple thousands, 3,000, 4,000, something like that. But my N right here is 60,000. My D here is 784. So this has happened to our situation that we actually choose our big D right here is significantly smaller than 60,000. So that's why for the kernel trick, we don't actually need to work to calculate this, I mean, 60,000 by 60,000 matrices. We can just work on this Z part, and the Z is a couple thousands, which is much more manageable than N. N is way too big to be used on the kernel trick. So everything right here for 3.1, I will guide you through to and derive everything one by one for this part right here. So, and what does that actually means if we just choosing this Z in a very particular way, the Z that we choose right here is basically square root of 2 of cosine of W and X inner product plus B. This W here is actually what follows the Gaussian distributions. B is a uniform distributions between 0 to 2 pi. if we choosing these things in this way, and we can show the expectation of this z and zx and zx prime actually will be this kernel and the Gaussian kernels and between x and x prime. So this is a very, very important fact. So we can actually use this factor for this and random projections. So this is the techniques of the random and the projections, and project as everything into into the dimension that is lower than n, but still bigger than the original dimension, which is 784. If you project everything into that regions, and you can show on average, this is can be equivalent as just taking the Gaussian kernels. So right here, and you can see this is what we are getting here. So this is basically if you're using all this like theorem that you prove, that you can show right here. If we're taking this zx, which is and given right, and given in this way, and you already did that in the homework. This is equivalent as a like RBF kernel, which is a Gaussian kernel. So basically, the expected value of inner product between these like random, and this is called random Fourier features, is actually the RBF kernels. So this is very significant, turns out. So we don't actually need to work on the and the kernel tricks explicitly. We can using this kind of like, and random Fourier features actually can help us and implicitly to work on and the kernel tricks. And this is concentration bound, which is fairly straightforward. All we need to do is just plug in the holding lengths like inequalities, and you should be able to get this and very explicitly. One of the things for the last part is I want you to actually verify and verify these theorems. So we already have this data here, and I told you how to and what we do this like feature transformations, which is cosine of like gx plus bg right here. You can think about is under the random matrix, but the difference is here is this is and each of the w right here, it's, and if we stack and each of w right here, so this will be my weight and of g. Okay, so this is just for and one w right here. So because this actually and it goes to and one scalar here, but in our homework and we show this is actually mapped into like and map and is actually mapped to like random vectors and rather than the random scalar here. So if we do everything right here, you can actually show this whole thing while scale behave like this and all. And of course, you need to show what is this gamma right here based on the based on this Gaussian distribution that you choose, and also this is also the uniform distributions for the B. Okay, so and you can actually calculate this like gamma right here. So if you need it. So with that, you can using this data and the parameters to actually design an algorithm to verify whether this and a statement is a true or not, right? So, and so if this statement is actually true, that means our method is basically equivalent to work on the Gaussian kernel and SVMs, right? So this is something that we already be doing in process, but we didn't like teach the SVM yet. We are just using a very smart trick and implicitly just applying this kernel SVMs. Okay, so that's why, and of course, this whole thing will might take a little bit time. You don't need to use all the data, so, and you can and just take a portion of the data to actually to illustrate this idea. All right, so that's all for some like tips and tutorials for the homework 2. Again, I would suggest everyone to start early, and this is very important to understand what is going on underneath of it. Okay.